Hello, everybody out there. It is your favorite Canadian physics professor, Dr. Rehse, here to talk to you today. We got another great topic for your fun and fabulous DoD STEM Saturday pleasure. Today, we are going to be talking about a really interesting topic, nuclear power, energy and power. It's a topic that's on a lot of people's minds lately. So not a lot is known about nuclear power, though. People kind of know the words, but they don't really know what this is all about. So let's jump into this and see what this nuclear power is all about. So of course, as always, we want to start off with our land acknowledgement statement. I'm so pleased to be a representative of the University of Windsor and to be able to share our thoughts and the way we feel about our university with you all watching this from home. And as you know, the University of Windsor sits on the traditional territory of the Three Fires Confederacy of the First Nations, which includes the Ojibwa, the Ottawa, and the Potawatomi. We respect the longstanding relationships with First Nations people in this place. The 100-mile Windsor-Essex Peninsula and the Straits are Le Detroit of Detroit, and we're so pleased to acknowledge our land and to share that with you all. So if we're going to talk about nuclear power, what's the deal with nuclear power? Well, let me start off with something that is pretty hard to argue with. We need electricity. I think this is an obvious statement. If you're watching me right now, you are using electricity. You're watching on your phone or a computer, or somehow you're seeing something that's powered by electricity. So it's a pretty obvious statement. And here's a person charging their cell phone in the wall. And here's a picture of electricity. I just wanted to put this on there and just remind all you kids out there that are watching, if you have something like this in your house, that's a bad idea. All right. You can't have this many cords plugged into a power bar. And people sometimes do this. Bad idea. This will overload your system. These things could overheat. This could start a fire really easily. So if you've got something like this in your house, get rid of it. You've got to do something better. So, but we need electricity, right? That was my main point on that. So where does it come from? All the electricity flowing out of this plug here, flowing into your phone, going through this tangle of cords here. Where does that electricity come from? Where is electricity made? Well, the reason I'm talking about it with you all today is that electricity is generated using physics. You all know I'm a physics professor. I love physics. Physics is the reason electricity is being generated and brought to your house. So most electricity that we're using today is generated. It's the word that we use. We don't say we make electricity. Electricity is generated, and it's generated in an instrument or device called a generator, and it uses a physics idea called induction. So here's an idea of a schematic of what a generator looks like, and then here's a nice graphic from the good people at Briggs & Stratton showing kind of the interior of their generator. So, and then here's another cutaway view of what a generator looks like. Essentially what you're doing is you are somehow, some way rotating a loop of wire, and that's shown here with this red and blue kind of cable here, and you're rotating it in a permanent magnetic field. So electricity is kind of, to make it, is two things. It's a magnetic field that exists somehow, and then somehow a loop of wire is turning within that magnetic field, and then the magic of physics happens, and that generates electricity, okay? And understanding how that happens is a really interesting topic, and we're not gonna have time to get into the physics today, but if you just roughly know how a generator works, that will help. And so again, here's a big generator, and you can see inside this generator, they're showing the schematic of there's a main rotor, right? So the rotor is the word in a generator for those loops of coils that are produced by the coil of wire in the stator. So the stator is the stationary bit that generates the magnetic field, and the rotor is turning without it. And then these things are really big, right? But generators all work on the same physics principle. That's why physics is so universal. It applies if it's a small thing, it applies on the scale of a huge power plant. So what do you guys need to remember coming away from this? The generator. How does the generator works? We turn a loop of wire into some kind of magnetic field. Bottom line, we somehow need to rotate a loop of wire in a magnetic field. So the magnetic field will come from magnets that we have and put in there, but something's got to get that loop of wire spinning inside that field. How are we going to do that? So I guess if what you have is lots of human power, you could have a little guy like this just churning away like crazy on this little crank and crank, 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 and by hand you're cranking the wire inside the magnetic field. Then you yourself would be generating electricity, and that would work probably for a very, very small amount of electricity. But this is probably impractical to hire people all over the world to turn little coils of wire in a magnetic field. So that's probably not going to work. So how are we going to do that? Well, before I get to the power plants and nuclear power, your car does that all the time. There is a device in your car, which maybe some of you know about. It's called the alternator. Okay, the alternator is a generator. So I'm showing you a picture of what an automobile alternator looks like. Well, look at all these loops of wire in there. Okay, so the alternator is actually generating electricity to charge the battery in your car and to generate other forms of electricity in your car. And it uses the gasoline engine to turn the rotor. The rotor is the loop of wire that turns inside the magnetic field. Every car has an alternator, for the most part, every car. I'll get to that in a second. The alternator is turned by the gas engine, and it's generating electricity all the time. So that's why the battery in your car should not die. It's always being recharged by the electricity generated in the alternator, which is spun by the gas engine, because you're getting that rotation from somewhere else. Now, the generator in a Prius is a little bit different. So here's an example, again, from the good people at Toyota, of what the interior of a Prius engine looks like. It's a hybrid because it has an internal combustion engine, but it's also got this generator form over here, right? So you should see something now. It should be starting to look kind of familiar. You see all these copper wires. This orange colored stuff is copper wire. You know that this is a generator. It's spinning and it's generating electricity. So the hybrid car, the beauty of that is it actually uses the motion of the wheels, not the gas engine, to turn the rotor. So when you apply the brakes, the rotation of the wheel can be used to turn the rotors of the generator, which then generates electricity and creates drag on the turning of the wheels to slow you down. So we call that regenerative braking. So there you're actually using the motion, rotary motion of the wheels to turn the rotors inside the generator. And that generates electricity, which then recharges the main hybrid battery in a hybrid car. So that works really well on a small scale, the type of power required by an automobile. But that's not going to work on an industrial scale. So how do you spin the rotor inside a generator on an industrial scale? Well, one obvious way of doing it is windmills, right? And here's a schematic of a windmill. They're turning. That looks obvious. The wind blows. As the wind blows, the windmill turns. What that windmill is doing is turning a rotor inside a generator. So up in the head of that windmill, it's turning a loop of wire in a magnetic field, and that's going to generate electricity. We also have what are called hydroelectric plants. All right, so in a hydroelectric plant, it is the flow of water over a dam which gets this rotational motion going, right? So you're showing a nice aerial view, and a hydroelectric plant is really a dam. They create a lake, and then when they open the gates of that dam, the water flows through, and as the water falls down, it turns over turbine blades. The turbine blades start spinning, and that's what turns the rotor inside a generator. So a lot of electricity is generated in hydroelectric plants. They have to be located near large bodies of water. Most of the electricity generated today in the US uses boiling water, which is steam, to turn a turbine, which then turns the generator. And this is why most of our electricity is generated in gas or coal plants. When I say most, if you look at this schematic over here, you can see that gas is about 23%, coal is about 38%, hydroelectric about 16%. So still, it's over 50%. So most of the electricity generated in America comes from this type of power generation. You have water, you boil that water somehow, and when water boils, it becomes steam. That steam is pressurized, and then the high pressure steam blows over a turbine, which is a little bit like that windmill you're seeing on the side of the screen, but not quite. But it's the high pressure steam blowing across the turbine that gets the turbine, which is like a giant fan spinning, that turns the rotor inside a generator. That generates electricity, right? So the physics remains the same. You have to rotate something in a generator to get it going. And in the case of most electricity generated in North America, it's the boiling of water, high pressure steam turbine that does that. So What does a steam turbine looks like? It looks like this. They are massive pieces of apparatus. So here are two power plant workers standing next to one turbine, and power plants will have multiple turbines in there. This is what the interior of a turbine looks like. And then this is just a close-up of those turbine blades. So if you look really closely in this image, they look like fan blades or propeller blades in a turbine engine, and that's what it is. So I'm showing a little animation over here, which shows you the high pressure steam is coming in red. It's coming from right to left down here. The high pressure steam blows out with a lot of force. It blows onto these turbine blades, and the turbine blades are canted just like the blades of a fan. And that high pressure steam gets that turbine spinning really, really, really fast. All right, so that's what a steam turbine does. It takes pressurized steam and converts it into rotary motion. And then of course you just hook up one end of that turbine to a generator. Now you've got this rotation motion, which is then going to rotate a giant rotor inside a generator, and that'll produce electricity. So the same kind of thing that's happening on the small scale in your alternator, it's happening on a huge scale in a power plant. So again, what do you need to take away from this? Bottom line, we somehow need to boil water to turn a turbine. All right, that's so I gave you two bottom lines. You have to rotate something inside a magnetic field to generate electricity. And the way we do that is with high pressure steam over our turbine. So now we just need to boil water to turn a turbine. How are we going to boil water? Here's a picture of boiling water. How are you going to do that? All right, you guys have all seen boiling water boiling on your stovetop. Well, how do you generate that much steam under high pressure? Nuclear power is a great way to do that. A lot of people think that nuclear power, here's the first misconception, that it's using radioactivity to heat and generate electricity. Not at all. All a nuclear power plant does is generate heat to boil water from natural radioactivity. Highly radioactive sources, by virtue of the nuclear processes going on inside of them, get hot. They get hot enough to boil water, and it just happens all on its own. You don't have to burn anything. This is why it's going to be super clean, because in all the other processes, you're burning something like a fire to boil the water. Here, you don't have to burn anything. The nuclear material gets hot all on its own, hot enough to boil water and create steam. That steam is pressurized, and it turns a generator. It turns a turbine. The turbine turns the rotor inside a generator. That generates electricity. That's all a nuclear plant is doing. It's using heat from naturally radioactive things to boil water, which is a way better option than boiling or burning tons of coal. This is a completely clean process. There's nothing being burned in this process. So, in the words of Marty McFly, one of my favorite characters from Back to the Future there.
Plutonium, wait a minute. Are you telling me that this sucker is nuclear?
Oh yeah, baby. This sucker is nuclear. That is right. So this is what nuclear physics is all about. So of course, those of you who know the great movie Back to the Future, Marty McFly traveling backwards through time in a nuclear powered DeLorean shown over here on the left. And just for fun fact, here is yours truly sitting in the driver's seat of a nuclear powered DeLorean, ready to travel backwards in time in the nuclear powered DeLorean. So that's me right there. So just thought that would be fun. So one of the reasons I got interested actually in this topic is that I'm talking to you from Windsor, and you all are sitting over there in the Detroit area, and we actually live really close to a nuclear power plant. It's down here on the Google Maps I've indicated. This is the Enrico Fermi 2 NPP nuclear power plant, located right on the shores kind of Lake Erie down there, like a large body of water needed. Here's an aerial view. Again, this is all obtained from Google Maps, so there's nothing private or confidential about this. I just went on Google Earth and got these images. This is the Enrico Fermi 2 nuclear power plant. And you can see we're going to talk about this is what's going on down in the reactor and the cooling towers here. We'll talk about what's kind of happening in a power plant in a little bit, so when you see this distinctive shape. But we're all very, very close to a nuclear power plant. And I don't think a lot of people know that. And I don't think for sure they don't know how it operates. So I think we really need to understand what's going on, because this is a really efficient way to generate electricity. So it just got me thinking that that would be a neat topic to talk about. I also wanted to mention it because Fermi 2, 2, it's called, if you live in the Detroit area. So it's the Enrico Fermi 2, but we just call it Fermi 2 around here. Why is it Fermi 2? Well, that plant is named after the great famous Italian physicist Enrico Fermi. So here's a picture of Enrico Fermi as a younger gentleman right there, looking at one of his physics experiments, and really kind of one of the fathers of nuclear power, I would say. So nuclear power was basically the birth of the nuclear age happened around 1942. Enrico Fermi and his team of physicists built the world's first nuclear reactor in 1942. And where did they do that? At the University of Chicago, under the football stadium. So this is kind of what it looked like. Here's a picture of the football field at the University of Chicago. And I believe it was actually built in the squash courts, which are located underneath the bleachers, underneath the stands at the University of Chicago. And then this is kind of a schematic of the very first artificial nuclear reactor. They call it the Chicago Pile 1. And it's the first human-made self-sustaining nuclear chain reaction happened on this day in history, 2nd December 1942. They call it the pile, and I've heard two different stories on that. Sometimes because you can see this thing right here, it just looks like a giant pile of bricks and lead and shielding and stuff. It's like, what's that? That just looks like a pile of stuff. But I've also heard that it comes from the Italian word for battery, for pile. So Fermi was an Italian, and they would have called this thing that generates electricity or generates power on its own the pile, the battery. So, but pile may have been converted to pile because they were working in America when they did it. But so nuclear power, man-made, human-made self-sustained nuclear power is really pretty new. 1942 is basically the first time this was ever done in human history. And that reactor and all the reactors that we're using now use nuclear fission. There's another type of nuclear reaction called fusion. That's what powers the sun. And I'm not going to talk about that. Maybe a future lecture, because that's a really interesting topic. But today, all we're talking about is nuclear fission. Fission generates heat. What is fission? Fission is the generation of heat that produces energy by breaking a large nucleus. So this is just a picture cartoon of what a large nucleus like the uranium nucleus looks like, and it breaks it into smaller nuclei. So when you hear the word fission, fission just means something big gets broken up into smaller things. And when the big thing gets broken up into smaller things, it produces the smaller things and heat. Energy. That energy is going to be used to boil water. It just comes out of the nuclear physics. You don't have to do anything to it. The heat comes along for the ride. That's nuclear fission. Heavy nucleus becomes lighter nuclei and extra energy in the form of heat. And the word that the physicists used, fission, actually is taken from the biological context. So here I'm just showing a video clip of cells undergoing fission. So that's a biological term that was actually known before the physics part of one thing splitting up into many other parts. When you see cells reproducing like are happening in this video, you start off with 1 or 2 cells, and those cells bud and divide and bud and divide. So they become a greater number of smaller things as they divide, and that's called fission, that one thing splitting into 2 smaller cells. So the physicists took that name and applied it to this nuclear process that we call fission. All right, so that fission is going on all the time in uranium and plutonium and things like that. All we need to do is actually control it. So it happens naturally all on its own. We need to build a reactor around it, and we need to control it. So control of a nuclear reactor is actually pretty simple. So this is a schematic, rough schematic of a pressurized water reactor. You have all this nuclear fuel inside in the form of uranium fuel rods. It's purified uranium that nobody else can obtain, and it goes inside the reactor, and it's pure enough of this radioactive uranium that it wants to generate a lot of heat. These fuel rods that I'm showing in orange and yellow and red here, these are generating heat due to the natural nuclear fission. But we need to control the amount of heat they generate. And when you control the amount of heat, then you control the amount of steam you make, which controls the amount of electricity. And we do that with boron control rods. So these control rods that I'm showing here in black can move in and out of the nuclear reactor. It's just like an accelerator pedal in a car. You press the pedal down, you want to go fast. You put no pressure on the pedal, you don't go at all. The control rods, you put them all the way in, nothing happens. As you pull them out slowly, the reactor starts to get hot and starts to generate steam, which generates electricity. So by moving control rods in and out of some stationary uranium fuel, that's all it is, that heat that's generated from the natural nuclear fission is going to boil water, and you can see that in blue here. So the water becomes steam. The steam does become pressurized. We have to put it through a pressurizer and just convert it from regular steam to high pressure steam. That high pressure steam is then pumped into a turbine, and then the turbine will spin, and that generates electricity in the generator. So it's not that complicated process. Here is a cutaway schematic of a person, you can see the scale here, standing in front of what a nuclear core looks like. They're usually about 30 feet tall. So you can see about the size of 30, 40 feet tall, something like that. This is not a new a real nuclear reactor. It's just a cutaway, but you can kind of see what the core looks like, this thermal shield, and this would be the nuclear core right in here with all the fuel rods, and then the control rods able to be brought in and out from the top, which is kind of like the accelerator. This is what a nuclear reactor core looks like when you look down into it. I've actually had the opportunity to do that in my lifetime. It's actually really, really cool. This is not a false color image. This is a real image. You are looking down into the nuclear core through the pool of water that it's sitting under, and the natural ionizing radiation produced by the nuclear decays produces this blue glow in the water, this Cherenkov radiation that we call it. It's this beautiful deep blue color, and it just does it all on its own, and it's completely quiet because there's no moving parts in a nuclear reaction. It's just the atoms and nuclei doing what they do, generating this energy. This is, you note, the top is off this reactor. It's completely safe because it's all underneath that water, and the radioactivity can't come out in this form that in the way it's operating right now. So here's another picture. Again, not false colored. This is the actual color. It's this beautiful blue color that the water kind of glows at in the presence of all the ionizing radiation from the nuclear reactor, this Cherenkov radiation. So it's just a beautiful, beautiful thing. So that's what it looks like inside. You guys are probably never, unfortunately, going to get that close to a reactor, but you're going to see things like Fermi 2 from the outside. So what would you see? Well, in a nuclear reactor, as you're driving by on the highway, you will see these things. And what you will see are these guys, but this is not the reactor. So now you're going to know something your parents don't know. The reactor core is actually over here in this small building where the reactor core is and where they're generating the electricity. It's over in these buildings right here. These things that you see, which stick up way up above the landscape, these are actually cooling towers. And they're cooling towers because they're getting rid of extra heat. There's a lot of heat generated in this process. And after you've boiled the water and turned it into steam and high pressurized steam, and it's turned the turbines, you still got a lot of heat left over, and you got to cool it off. We cool off that water by letting it drizzle down the outside of these cooling towers, getting rid of extra heat. The thing about these cooling towers is then when you always see this white puffy stuff coming off the top, here's the beauty of nuclear power. That is just steam. That is not pollution. Coal plants and oil plants are burning things, and they're putting, and everybody's worried about the pollution that it puts into the air. Sure. Nuclear power plants do not generate any sort of pollution in that way. This is just steam coming out of it, just water. It's all clean. So important thing to know when you see this at a nuclear power plant, that is just steam, not pollution. You might see one of those nuclear power plants as you're driving around your car. You might see one of those in Springfield if you watch The Simpsons as well. Here's our favorite nuclear technician, Homer, down here spinning around in the nuclear control room. And here's actually a screen grab I got of the famous Springfield nuclear power plant where Homer works. And if you look at the drawing that the artist did, it looks a lot like the real nuclear power plants. The core's over here. It's got the same buildings. And again, they're showing the cooling towers over here with this white stuff coming out of this. And next time you watch The Simpsons, and if you see this, you can tell your brother, your sister, your parents, hey, that stuff coming out of the top of that, that's just steam. That's not pollution. That's steam. And so the artist on The Simpsons actually got it right. You might actually see nuclear reactors in more places than you might be aware of. So it's not just these giant roadside reactors generating electricity for millions of people that use nuclear reactors. Here's an article that I grabbed from Forbes magazine, December 23rd, 2019, article called How the US Navy Remains the Masters of Modular Nuclear Reactors. It turns out the US Navy is a nuclear powered Navy, which means a lot of our ships actually run on small modular nuclear reactors. We certainly have nuclear powered submarines shown here, nuclear powered aircraft carriers shown here. They don't look like those big Simpson scale nuclear power plants. They are much more modular. And here's kind of an outside schematic of what a modular nuclear reactor looks like. But, you know, these nuclear reactors are small, portable, safe. They've been used for decades in the nuclear Navy, allowing the US ships to sail all over the globe and never have to stop for refueling because they don't burn oil, they don't burn gas, they don't burn coal. They're nuclear powered. And one last application, the new Mars rover uses nuclear power as well. All right, we have the new Perseverance rover roving around Mars. How do you think it gets there? Do you think it's burning gasoline to move around Mars? There's no oxygen on Mars. It couldn't burn gasoline, can't burn coal. Where's it going to get its power from to power the wheels and to run all the electronics? It has a nuclear reactor. So I took this quote from mars.nasa.gov. Perseverance carries a radioisotope power system. Power system produces a dependable flow of electricity using the heat of plutonium's radioactive decay as its fuel. So the multi-emission radioisotope thermoelectric generator, which is kind of shown here, converts heat from the natural radioactivity decay of plutonium into electricity. So on Perseverance, they are not using radioactivity to boil water for steam. That's only for the large turbines, but they are using the heat generated from natural radioactivity to produce electricity. It does it in a different thermoelectric way, and that's a talk for a different day, but certainly it is a nuclear battery. If you want to be completely upfront about it, what powers Perseverance? That's a nuclear battery. It's not a chemical battery. It's not a rechargeable battery like you have in your phone. It's a nuclear battery that the heat from radioactive decay can generate electricity, allowing Perseverance to roam around the surface. So that's all I have for you today. Nuclear power, right? Here's a schematic on the table. You should learn more about it if you are interested. But the upshot of the entire message and the talk is all a nuclear power plant is really doing is using radioactive material to generate heat, and that heat is used to boil water. And boiling water becomes steam. Steam is pressurized. It turns the fan blades of a turbine, which then turns the rotor of a generator, which is just the way all the other power plants work. So people just think nuclear power plant is something really, really different. It's not. It's just doing the same thing all the other power plants are doing. It's just doing it in a clean way because you're not producing any CO2 and you're not producing any burned byproducts by burning coal or oil or even natural gas to generate that steam. So it is a really, really important option and one of the tools that we can use for generating power as we move forward into the future. So thank you so much, everybody. I hope you enjoyed this talk and learn a little something about nuclear power. I look forward to talking to you next time. We've got a lot more topics coming up, but I think for now, that's great. So have a great day, everybody, and I'll take your questions once we finish this talk, all right? I'll talk to you next time.